Hello everyone, it's Mrs. Jennison here again. I'm an Associate Director for Outward Grange Academy's Trust. Welcome to today's lesson. Today's lesson is on corrosion and prevention, and this lesson is for triple science students only. As with all of our lessons, it would be really useful if you had a pen and a piece of paper so that you could work through the activities with us as we go through the video. Our challenge today is to be able to describe how corrosion is caused and how to prevent it. Our aspire is to be able to explain how different methods of corrosion prevention work. So, corrosion is the destruction of materials by chemical reactions with substances in the environment. Rusting is a common example of corrosion. Both oxygen from air and water are necessary for iron to rust. So here is an example at the moment on the screen of corrosion in aluminium, as a lot of substances corrode, but rusting, as seen in these two examples, is specific to iron. Now, what I'd like you to do is to use the images on the screen to suggest which conditions would increase the rate of rusting. Okay, so you may have noticed that both images are actually near the coastline and one of the images actually inside of the sea. That is because salt is a catalyst for rusting. Oxygen and water are needed for rusting, but salt will increase the rate of that reaction. I'm going to insert a video here that explains this in some really good details.
Let's think about cars for a moment. The car that you've had in mind was likely painted with your favorite color. The paint is not only there to make your car look pretty, but it has a more important purpose: to prevent rusting. When iron and steel are exposed to oxygen and moisture, rusting will occur. Rusting describes the corrosion of iron and steel. The term corrosion is used to describe the breakdown of a metal when exposed to the environment. When we say a metal corrodes, we mean that it has reacted with water and oxygen from the environment to form their respective oxides. Rusting can be very costly if we have to constantly replace these items made of iron and steel. Rust can be prevented if we paint the areas exposed to oxygen and moisture. This is done on many bicycles and cars. Another method to prevent rust is by placing a layer of oil or grease. This is done on many bicycle chains. It helps lubricate the moving parts, which reduces friction and slows down the rusting process. Another way to prevent rusting is a sacrificial protection method called galvanizing. Have a look at this reactivity table. Zinc is more reactive than iron. When exposed to oxygen and moisture, zinc will corrode faster than iron. So if we put them together, zinc protects iron but is sacrificing itself, hence the term sacrificial protection. This method is applied to prevent rusting on ships. The oxidation of zinc can be described using this following equation. So besides preventing rusting, there is another advantage to this galvanizing process. The formed zinc oxide layer can be removed, and the freshly exposed zinc can corrode once again, thereby further protecting the iron or steel hull.
So now that we've seen the video, I'd like you to state the conditions metals need to be exposed to for rusting to occur, specifically iron, and then I'd like you to give the methods of rust prevention that were named in the video. Okay, so the conditions metals need to be exposed to for rusting to occur are oxygen and water, and salt can be a catalyst. Remember that rusting is only in iron. The methods of rust prevention named in the video were paint and coating the object in oil. Both of those prevent oxygen and water getting to the object. And also galvanizing or sacrificial protection, and we will be looking at that later on in the video. So there's also an experiment which you can carry out in a lab that can investigate the factors that affect rusting. So you can expose nails to different conditions and measure the rust. You can weigh the nail to see if it's gained mass due to reacting with the surroundings. So I'm going to insert the video looking at that experiment here. This is commonly asked about in exams, so it's definitely something that you should have knowledge on.
We can demonstrate this using a simple experiment. Place an iron nail in 4 test tubes. Fill one with regular tap water until the nail is submerged. Fill another with regular tap water and add half a spoonful of sodium chloride, regular table salt. Shake from side to side to ensure that sodium chloride fully dissolves. Fill the third test tube with recently boiled water and add a thin layer of oil. When we boil the water, we remove any dissolved oxygen, and the layer of oil prevents any oxygen from further dissolving. In the last test tube, add a spoonful of calcium chloride. Calcium chloride removes moisture or water. So in the first test tube, the nail is exposed to oxygen and moisture. In the second test tube, the nail is exposed to oxygen, moisture, and salt. So in the third test tube, the nail is only exposed to water. In the fourth test tube, the nail is exposed only to oxygen. Stopper all 4 test tubes with a rubber bung and let stand for a couple of days. You will find that the nails in the first and second test tubes have rusted. In particular, the nail in the second test tube has rusted more than the nail in the first test tube, and the rust has likely flaked off. You may see a reddish-brown precipitate at the bottom of these tubes. The nails in the third and fourth test tubes have not rusted. So what has happened here? The iron has undergone an oxidation reaction, forming hydrated iron trioxide or rust. Salt and acid act as a catalyst for this reaction, which is why the nail in the second test tube formed more rust than the nail in the first test tube.
I've put a table on the screen that you can use to record your results from this experiment. Now, you've just seen this on the video, so what I'm going to do is I'm going to give you some time to complete this table based on the 4 test tubes in the image. So you've got test tube A, which is boiled water and an oil layer, test tube B, which is salt water, test tube C, which is air, and test tube D, which is air and calcium chloride. I'd like you to tell me whether the nail would rust in each of those test tubes, and also try to explain why. So, the nail that was in the conditions of boiled water and an oil layer would not rust. The reason for that is when you boil the water, the oxygen is removed from that water which was previously dissolved into it, and the oil prevents any more oxygen dissolving into that water. The nail that was in tube B, that was salt water, would have a lot of rust present, and if you were measuring this as mass, that would have the highest mass change. The reason for that is oxygen and water are both present, and the salt will speed up that reaction. It's a catalyst. The nail that is in tube C that is exposed to air will have some rust present, as oxygen and water vapour are both present in air, but nowhere near as much as the one that was in the salt water. And the nail in tube D will not rust, and the reason for that is that calcium chloride will absorb water, and it will then remove any water from the air around the nail, so it won't have water present. And because that tube is corked, no more water will get into it. There is oxygen present, however, but for a nail to rust, it needs oxygen and water present. Now, I told you earlier on that we'd look at sacrificial protection later on in the video, so I suppose it's time for us to look at it now. Now, sacrificial protection links to the reactivity series of metals, and there is many ways to learn this, and we cover those in a previous video. Now, if you attach a more reactive metal to a less reactive metal, the more reactive metal will corrode, and that leaves the less reactive metal in perfect condition. So let's say I was to attach a metal to a lead pipe to prevent corrosion. If you look at the reactivity series, I could use any of the metals that are above lead in that reactivity series. I wouldn't use sodium and potassium because they react with water and it's a lead pipe. I would probably use something like aluminium because it's very reactive compared to lead. And the bigger the difference in that reactivity, the better the protection is for the metal that you do not want to corrode. A really good example of where this is used is in oil rigs. Now, oil rigs are typically steel, which is made out of iron, and they are at sea. So they are exposed to all of the elements that you do not want these oil rigs to be exposed to. We've got oxygen, we've got water, and we've got salt, which is going to speed up the whole rusting process. So to prevent that happening, we attach one lump of metal to those steel legs. And actually, the metal they use is magnesium. And that's because magnesium's got a very big difference in reactivity to iron without it being so reactive that it's going to react with the sea itself. The magnesium block will need to be replaced as it will corrode very quickly, but that's cheaper than replacing the entire steel structure of that oil rig. It's also much cheaper than painting or greasing the legs to protect them, as that's not realistic once the oil rig is already in the ocean. It's very fast and easy to do. Now, this method is used on underground pipes, ships and large structures that are costly to replace and very complicated to paint. Now, as I've said a few times, sacrificial protection works best when the metal attached is much more reactive than the metal you want to protect, which is why we used magnesium and not zinc. Ideally, like I said earlier, we could use potassium, but because potassium reacts with water, that would cause us a lot of issues. Magnesium's pretty much as reactive as we could go in this instance. Okay, so it's time for another exam question. If you need any extra time on any of these questions, remember that you can pause the video to get that. It's those test tubes that I spoke about earlier with a few extra added in. So let's read through it together before we give you time to answer this. The figure shows 6 test tubes a student set up to investigate the rusting of iron. This is the method that they used for each test tube. So they measured the mass of the nail using the balance. They left the nail in the test tube for 6 days, and then they measured the mass of the nail after 6 days. Remember that if the iron nail rusts, that would increase the mass because it's reacting with its surroundings. So we've got 6 test tubes. The first 3, test tube 1 has water in it and it's partially exposed. Test tube 2 has dry air. Test tube 3 has water with oil over the top of it. Test tube 4 has a painted iron nail. Test tube 5 has an iron nail which is painted but with a scratch. And test tube 6 has a galvanized iron nail which is also scratched. So we have a table now with the students' results. The first thing they would like you to do is tell them the resolution of the balance. Then they would like you to calculate the difference in the percentage increase in mass after 6 days of the nail in test tube 1 and the nail in test tube 5. Once you've done that, they want you to give your answer to 3 significant figures. As I said earlier, if you need extra time on this question, feel free to pause the video. Section of the exam question, I'm not going to give you a timer. You should allow around 6 minutes to answer this after I've finished reading through it, but there's a lot of information to process, so I don't want to rush you. You can see that I've given you the students' results and the diagram of their experiment again. They'd like you to use those results to draw conclusions about factors affecting the rusting of iron, and to include an evaluation of the effectiveness of the different coatings at preventing the rusting of iron. So you should link the mass change to the conditions that that iron is under and explain whether they have rusted or not, and then use that information to evaluate those coatings. Remember to pause the video now, have a go at answering, and when you're ready, resume. Okay, last question. Rust is hydrated iron 3 oxide. They'd like you to complete the word equation for that reaction. Okay, so the resolution of the balance was 1 times 10 to the minus 2 grams. Now, there's an example of the working out on the screen at the moment for the percentage change. Remember that the percentage change is the change divided by the initial times 100, which meant the percentage change for test tube 1 was 5.44%, and the test tube 5 was 0.854%. So essentially you're then calculating the difference between those two percentage changes, which would give you 4.586, but to 3 significant figures that would be 4.59. Now, for the evaluation, we're always aiming for a level 3. And for a level 3 answer, it's a detailed and coherent conclusion, which is based on the evidence together with an evaluation. So essentially, you're making relevant points across the board using the evidence you've got and then provide that judgment at the end. So let's have a look at the indicative content. So the nail rusted in test tubes 1 and 5. Test tube 1 and 4 both contained air, oxygen and water. The nail did not rust in test tubes 2, 3 and 4. Test tube 2 had no water present, test tube 3 had no oxygen present, and test tube 4, the paint stopped the rusting because it prevents the oxygen from getting to the nail. Test tube 6, the scratched galvanised nail did not rust. Test tube 6, the galvanising must have stopped rusting. The conclusions: both water and oxygen are required for rusting. Coatings that prevent water and oxygen reaching the metal will prevent rusting. So there we're talking about the paint. But when the paint was scratched, the iron will come into contact with water and oxygen and therefore rust. This didn't happen when the nail was galvanised and scratched. Now, zinc is more reactive than iron, so when the galvanised metal is scratched, the zinc's reacting with the oxygen and water first, sacrificially. So for your evaluation, you're probably talking about how the oil and paint are both effective when they are intact, but the galvanising was the most effective coating because it prevents rusting even when scratched. And then to complete the word equation, it was iron plus oxygen plus water, which makes hydrated iron-free oxide. So that's everything for this video, and I will see you in the next one. Bye.